Chapter 27, Magnetic Field and Magnetic Forces, Lecture 2. Before viewing this video, you should review Chapter 27, Lecture 1. Now we got to a point that we can now discuss something called a velocity selector. It's a device that selects particles with specific value of velocity. Here's a diagram. The parallel plates provide an electric field, E, and there's also a magnetic field perpendicular to the page going into the page, B, and a particle of charge Q with velocity V is projected into the space between the two plates. And when it is in the region between the two plates, under the action of the magnetic field, there will be a magnetic force exerted on it. And if you use the right-hand rule, you can see the direction of this force, which is QVB, sine of the angle 90. So that will simply be QVB, and the direction is to the right. There's also the electric field in this region, and there'll be an electric force, and the electric force, of course, is going to be in the opposite direction, and the magnitude is Q times E. Now the magnetic force depends on the value of the speed, and at a certain value of the speed, these two forces would be exactly equal. So once we write our equation, you can just cross out the charge of the particle, and speed will figure out to be the ratio of the electric field to the magnetic field, which has a specific value. And therefore what it means that if particles have that specific value, they will go through the velocity selector undeflected. Now velocity selectors have a wide range of applications. Let's look at some of the applications. For example, you can use a velocity selector in a mass spectrometer. In a mass spectrometer, isotopes of an element are projected at the top there, at that point, and they go, as they pass through the velocity selector, if they're undeflected, they emerge at the point at the bottom at that point, with a certain value of speed, and these particles then at that point undergo a circular path due to the magnetic field present in that region, and particles with different masses perform circles with different radii. Why? Because if you equate the magnetic force to the centripetal force as we did before, you can just cross out the velocity and figure out the radius, and you can see the radius depends on the mass. Notice that different isotopes they all have the same charge but different masses. So therefore you can see that the radius would be proportional to the mass, because everything else in that equation, the right hand side of the equation, is the same except the mass. So if you now go and substitute for the specific value of the velocity that come out of the velocity selector, which if you remember is the ratio of E to B, then we get an equation that from this equation we simply can go and substitute, measure the radius r and substitute the value in that equation, and therefore calculate the mass, and from our calculation the value of the mass will tell us what type of the isotope we are dealing with. So that's why this is called a mass spectrometer. Another application is in the measurement of the ratio of the charge to the mass of the electron. This is called Thomson's E/m experiment. In Thomson's experiment, the equipment are in vacuum, capsulated in a glass capsule, and all the components are shown here. Electrons are accelerated from the region close to the cathode at that point, and they are accelerated between cathode and the anodes, and they emerge at the opening at A prime anode at that point. And because they have undergone a potential difference given by this value V, the potential difference provided by a source of EMF. So we can write down an equation and calculate the ratio of the charge to the mass of the particle. This equation is based on physics 50 work energy theorem, and also chapter 23 work done on a charged particle is the charge multiplied by the potential difference or the voltage that it goes through. So if we combine these two equations, we get this equation, and particle that we are talking about is an electron in the electron beam somewhere here. So let me show you one of the electrons that has a speed v, and the electron then moves into the region, into the velocity selector, where there is a magnetic field and an electric field at 90 degrees. The blue arrows show you the magnetic field provided by an electromagnet, and the red arrows show you the electric field provided by the parallel plates. And electrons then move through that velocity selector, and then we can just write down the ratio of the charge to the mass of the electron from the above equation, which is v squared divided by 2v. V is the potential difference, and if we adjust the value of the magnetic field and the value of the electric field in the velocity selector, then we can get the particles to move through it undeflected. We can do that by observing a bright dot that appears on the screen, and by adjusting B and E we can make that bright dot at that point to be exactly at the center of the screen. Center of the screen means those are particles that are undeflected, therefore must have the value of their speed to be equal to E over m. Alright, so you just substitute for speed, write it down as E over B, and you get this final equation. And on the right hand side of the equation you have all the quantities that you can measure fairly accurately, and therefore you can calculate the ratio of E to m, which is a well-known constant. It's 1.7586 times 10 to the power 11 coulombs per kilogram. This is a well-known experiment known as Thomson's experiment. Next, let's take a look at the magnetic force that is exerted on a current-carrying conductor. So here we have, in the diagram, we have a conductor of length L and cross-sectional area A. Current I is passing through the conductor, and you know that current is a result of the motion of charge carriers. Each carrier has a charge Q and has an average velocity known as the drift velocity. So you have to remember chapter 25 about drift velocity. Use your right hand rule, look at the direction of the magnetic field B, which is perpendicular to the page going into the page. Use your right hand rule and you will see that the magnetic force is pointing to the left, magnetic force acting on that charge carrier, on that particle. So we can write down what this is, write down this force, which is from our equation, is QVD, sine of the angle, multiplied by B, but the angle here is 90 degrees, so the force is simply the charge of the particle multiplied by the drift speed multiplied by the magnitude of the magnetic field. So that is the magnitude of the force exerted on that particle. But as you know, there are many charge carriers in that conductor. So if you want to know the force, the total force exerted on the whole length of that conductor, you have to multiply this force by the number of carriers that exist in that conductor. The number of carriers would simply be N, which is a density of the charge carriers, multiplied by the volume of the conductor. The volume is just the length multiplied by the cross-sectional area. So it's going to be A times L. That will give you the number. If you multiply that number by the force, then you get the total force. And the total force will just be equal to the number multiplied by force on one carrier. So just substitute for the force on one carrier from the above equation, and you get this equation. Remember from chapter 25, we had an expression for drift speed, which was in terms of the current, I. So it's the current divided by Q and A. Let's substitute for VD in the above equation, and we get this equation. And then you can see straight away that Q and A cancels with Q and A, and you get the magnitude of the magnetic force, total force exerted on the length of that, exerted on that conductor, which is the current flowing in the conductor multiplied by the length of the conductor multiplied by the magnitude of the magnetic field. Okay, so that force, of course, is going to be to the left, but we can just write down the cross product of two vectors to talk about the direction of this force by simply looking at this diagram. Write down your equation with the sine of the angle when the angle is not 90 degrees. Then use your right-hand rule and write down IL as a vector and B as a vector as a cross product of IL and B, and you get the direction of the magnetic force as shown in the diagram using the right-hand rule. All right, let's apply our idea of the magnetic force to what is known as a current loop. So if you have a current loop, as the name suggests, you have, in this case, in this diagram, we're showing you a current loop. The geometrical shape of the loop is a rectangle of length A, width B, and it's got a current flowing in it I, in the direction that it's showing. We place this loop in a magnetic field of magnitude B, and that's the direction from left to right. Use your right-hand rule to figure out the direction of the magnetic force exerted on the sides of this rectangular loop. And you will see that on the left side, the cross indicates that the force is perpendicular to the page going into the page. So we're using the same convention here for the force, same convention of direction for the force this time. And on the right side of the loop, you see the force exerted is acting perpendicular to the page and coming out of the page. The dot indicates that it is coming out of the page. Now, the top side and the bottom side, since the angle between L and B is 0, so there will be no magnetic force acting on the top side or the bottom side. All right, so let's write down an expression for one of these forces. It's just the current multiplied by the length of the conductor multiplied by the magnitude of the magnetic field multiplied by sine of the angle, which in this case the angle is 90 degrees. So it's simply IAB, the magnitude of the force. But notice that these two forces on the left side and the right side are not exerted at the same point. So can you see that this loop will rotate about an axis going through the dashed line? Because of the torque. So do you remember the equation for torque from physics 50? Tau is equal to B cross F. B cross F. That's the equation for torque. All right, what's the magnitude? It's just BF sine of the angle, but F here, remember, is IAB, so just substitute for it. So I get BIAB sine of the angle theta. And notice that B times A is actually the area of the loop. So we're going to rewrite our equation by considering A times B equal to uppercase A, the area of the loop, and your equation becomes IAB sine theta. Now, this quantity I times A has a name. It's called the magnetic dipole moment of the loop, and it's denoted by the Greek letter mu. All right, so it doesn't matter what geometrical shape the loop has, this will always be the same. The current flowing in the loop multiplied by the area of the loop is always the quantity called magnetic dipole moment. All right, rewrite the above equation in terms of mu, the Greek letter mu. So you get tau, the torque, it equals mu B sine theta, that's a magnitude. But we know that both the torque and the magnetic field are vectors, and we see that there's a sine of the angle involved here, so it's a good idea to rewrite this equation as a cross product of two vectors. For that purpose, we have to realize that mu is a vector. All right, what is the direction of this vector based on this cross product? Well, if you want to figure it out simply, just use the right hand, your right hand again. So if you use your right hand, this is the way to find the direction of magnetic dipole moment, mu. So you just simply curl your fingers in the direction of the current flowing in the loop, and your thumb will give you the direction of the magnetic dipole moment. As you can see, it's perpendicular to the plane of the loop. It's in the same direction as the vector that we associate with the area. All right, let's consider the torque exerted on this loop if there is a magnetic field applied from the outside. Let's apply a magnetic field at an angle theta to the magnetic dipole moment, as shown here. So B, the direction of magnetic field B, makes an angle theta with the direction of mu. And the torque will therefore be, now you can see where this equation, what this equation is applied to this diagram. You can see the torque, that's the magnitude of the torque. So you could say, okay, what about the direction? Well, you find the direction, you always write it as a cross product of two vectors. And if you do that, you can see the direction of the torque. Torque is in the direction that is always perpendicular to the plane that contains the other two vectors. That contains the plane that contains mu and b. And also always figured out by using the right-hand rule, as always. So your thumb is pointing upward. Here in this case, it means the rotation of the loop will be counterclockwise. Well, this idea is the basis of the operation of electric motors. Let's take a look at a simple direct current electric motor. As you can see in the diagram, the electric motor consists of two magnets with magnetic poles, the north pole and the south pole, provide a magnetic field in the direction shown, the blue arrow. And if you arrange a current to pass through the loop, this rectangular loop, you can see the direction of the current on the red side of the loop is opposite to the direction of the current on the blue side of the loop. And you can just simply use your right-hand rule. So straighten your fingers along the direction of the magnetic dipole moment. Curl your fingers toward the direction of the magnetic field, the blue arrow, in that direction. And your thumb will point along the direction shown by the red arrow, and that will give you tau, the torque. So that will tell you that the loop will rotate in a counterclockwise direction. And that concludes chapter 27.